Hello guys, welcome to this lecture series on Introduction to Machine Learning. Uh, the topic for today's discussion is support vector machines or SVM. So let's get started without any ado. Right, suppose we have distribution of data points like this, as you see on the screen. The data points clearly belong to two classes, red class and the green class. This is a two-dimensional visualization of the data. As like on the x-axis, we have one feature vector x1, and y-axis we have another feature vector x2. So for example, we want to classify apples and oranges based on their size and color, right? So the red ones are the oranges and the green ones are the apples, right? So how can we define a classifier for this particular data distribution, right? So as we can see, and we can tell that any of these three lines or any other line, like maybe like this line or this line or this line, is able to classify the data points correctly, right? But the question here is which line to choose. When we have, like for this particular case, we have infinitely many lines which can clearly classify apples and oranges. So which line to choose, right? So what support vector machines uses is the concept of support vectors, right? Support vectors, like these points are called support vectors, and we have something called positive hyperplane, we have something called negative hyperplane, then we have a maximum margin hyperplane, right? So let me define each of these one by one. First of all, if we are talking about two dimensions, and we are working in two dimensions, then we call any classifier, or like this, in our case this particular line, as a line because it is in two dimension. But when we talk in multiple dimension, three dimensions, four dimensions or more, then this classifier or this particular line which is classifying these two data points, or is distinguishing between these two data points, is called a hyperplane, right? Hyperplane. So any line in multiple dimensions is called a hyperplane. Now the way or the method to choose the best line or best hyperplane which separates these two data points is the concept of maximum margin, right? So out of all the lines that we saw in the previous slide, we will choose that line which gives us the maximum margin from these two data groups, right? So like this point here and this point here are the closest to the line, right, to this hyperplane. So we will calculate the margin of these closest points from the lines, and the line which gives us the best or the maximum margin from these data groups, or from these two data points, these corner cases, or you can say these closest points, we will choose that hyperplane to be the best classifier, or based on the maximum margin, right? So it is also called a maximum margin classifier, right? So like suppose this apple here and this particular orange here is closest to each other, like this apple is closest to this group, this orange is closest to this group. So this is also closest to all of the lines which are classifying these two groups. So we have to choose that particular line which gives us the margin, maximum margin. Margin is this distance plus this distance, right? This is how the line which gives us the maximum margin is the best fit, or you can not fit, but the best classifier, right? And these two vectors which are kind of responsible for defining the margin, in a way supports the best hyperplane, right? So these two data points are all called support vectors, right? So these are actually data points, but in machine learning terminology, all the data points are referred to as vectors, right? So these vectors, these two especially, are like kind of responsible for defining which line to choose out of all the possible options. So in a way, they are supporting, like, okay, supporting and defining which line to choose. That's why they are called support vectors, and hence we are calling this concept as support vector machines, right? So they have two sides. So one side is, like, we can call any of the side as a positive hyperplane, or any of the other side as the negative hyperplane. Conventionally, like, which side, so like anything which falls in this side is called positive, like will belong to the green class. Anything which falls on this side of the hyperplane is called a which will belong to the red class, right? And we have this, so that imaginary plane passing through the red support vector is called negative hyperplane, or the imaginary hyperplane passing through that this green support vector is called a positive hyperplane. Okay. So, like now, what is so special about support vector machines, right? So, suppose like in our example, we want to differentiate between apples and oranges based on their color and size, right? So, if you talk about these oranges, or like, or these cases which are like, it is very clearly visible that these belong to apples and these belongs to oranges, or you can like vice versa, any class, the red class and the green class. But the important part, or the crucial part becomes about these data points which are lying close to the margin, which are lying close to the hyperplane. Or I can say like, these are the cases, these are the corner cases, or the crucial cases where like an orange look is red in color, which looks more like an apple, and an apple is more orangish in color and it looks like an orange, right? So these are those cases where both of these it becomes difficult to classify these two data types. So in our case, it becomes difficult to classify which one is apple and which one is an orange. Like say for example, let's talk about this particular apple. So it's an apple, but it is like orangish in color, right? So it like based on size and color, it is more yeah, uh, closer to the orange group, right? Because it's in orange in color. And then talk about this particular orange over here, which is green in color. So like based on the size and color, it looks more like an apple. So the classification is very difficult, right? So the special thing about support vector machines is that like uh, support vector machines takes care of this bigger, easier to classify group also. But it also takes care of like very specially these corner cases. Support vector machine uh, defines the complete classification margin, complete classification hyperplane based on these two corner cases. Like this can be multiple corner cases, but in our example we have two corner cases, an apple which looks like an orange and an orange which looks like an apple. So the whole boundary, decision boundary, which is separating these two data points is defined by these two corner cases, right? So support vector machines is really great and really helpful to handle such corner cases or such difficult to classify data points, right? Now, so like for this example it was simpler. Now if we talk about some data point which looks like this, so the outer boundary, like outer circle is all red data points and the inner circle is all green data points. Now how can you classify this data point, right? Because the data points are not linearly separable here. Now how to go about it? There is no one straight line which can classify it, right? So I cannot classify with any of the straight line, and no, not a single, so no single line can clearly differentiate between the green points and the red points. Why? This is the called linear separability, right? So some data points or some data distributions are simpler. They any straight line can define or can describe the data distribution, or any straight line can distinguish between like green class and the red class. But some data distributions are not linearly separable, right? Where a straight line cannot distinguish or separate data into the specific classes, right? So how to handle non-linearly separable data points, right? So one way of doing it is to map into a higher dimension. Currently the data is in 2 dimension. If I can map it into a third dimension where I can just draw a line and separate the data points into different specific classes, then my problem is solved, right? So here like the problem is solved. This part it belongs to the green class, this part belongs to the red class. There is, I can draw a line over here. But in this case I cannot draw a line anywhere which can differentiate between my data points, right? So I can map it to a third dimension. Because it is 2 dimension, I can map it in a 3 dimension, and I will try to like maybe draw a line in those 3 dimension, right? So let's take an example. Suppose this is our data distribution, like red points, then green points, then again red points. There is also like for this data distribution also I cannot draw a straight line, right? I can draw something like this which can differentiate between red point and green point, but not a single straight line, right? So what can I do is like this. So I can first apply this function f is equal to x minus 5. So my data will move towards this side, okay, like this. Then I can do x minus 5 whole square. Just by practice, normal mathematics, I can do like this. By applying this function, I have changed the dimension of my data. So initially my data was only just on the x-axis. Now there is a y variable also, right? I added one more dimension to it, right? So this becomes the y dimension, right? So now my data is linearly separable, right? By applying this mathematical function, like my data remained same, but by applying some mathematical function, I was able to make it linearly separable, right? But just I used this normal mathematical trick. I just moved my data to like five points towards the margin, then I squared it, right? So squaring it allowed me to draw a straight line which can separate these two data points. So this is a very good way of solving problems, right? So similarly, suppose this is my data distribution. I want to make a draw. I want to make it linearly separable. I just want to pass a plane through it, which can clearly distinguish between both data classes. So I can apply any mapping function. So currently my dimensions are in two dimension, x1 and x2. I want to add a third dimension, x1, x2, and z, so that my like all of the green points are clearly separable from the red points, right? So the red points are lying in this x1, x2 plane, but all the green points have some positive z value, right? So and I can draw this hyperplane like this, which can clearly separate these two data points. Okay, so now I can again make a projection like this, so I can get a circular contour, or I can get a circular curve which is able to clearly classify the two green and red data points, right? So like for my for classification purpose, I went to the 3D space, but now once I got my plane, I can again project back to 2D space, and I can get a I can get a classifier for not a non-linear classifier, because it is not a linear shape. It is more of a circular shape, or you can say it is a curve. It is not linear, so I will call it a non-linear separator, right? It's a non-linear separator because it is non-linear. It is it is curved in shape, and it's a separator. It is separating between the green class and the red class, right? That's why it is called a non-linear separator. Right. Now there is a problem with using third dimension. Mapping to a higher dimension space can be highly compute intensive. So what is the meaning of compute intensive? Compute intensive means that you will need extra processing power. A lot of mathematical calculation needs to be performed, right? Suppose your data contains 10 lakh entries, and there are like 20, 30, 40 dimensions, and to transform the data from two dimensions to three dimension, you have to do some extra calculations, right? So you need to spend some extra time. Your processor needs to work some extra time, right? So it is compute intensive. And like suppose if you are talking about SBI, Amazon, or Flipkart, where the data is like really huge in crores, and the parameters are like, and the features are like 200, 300 dimensions, then it becomes even more compute intensive, like computationally costly. So we use something called as a kernel function, right? So kernel function is something which transforms your data into a higher dimension with a lesser cost. Okay, so very popular kernel function is the Gaussian RBF kernel, right? Kernel function. RBF is the radial basis function, right? So it is Gaussian. Gaussian means like of this shape, like a normal distribution, and radial basis function kernel. So kernel is something like I'm just passing my data through this kernel, and it is transforming me into different shapes, which is like easily separable, right? So this is what mathematically my a Gaussian RBF kernel looks like. K for kernel, X are my data points, right? L is my landmark, okay, landmark, and this function is e to the power negative of the distance between X data point and the landmark to the whole square divided by 2 sigma square. Sigma is the standard standard deviation that we have studied in the statistics and probability chapter, right? Let's look at about this function in a more detail, right? So this is what my function looks like. So X is my data point, L is a landmark, and this is the function, how it is transforming, right? Suppose I have the same data points as we have seen earlier, red and green data points, right? And I have chosen this point. The highest peak is at this point. So if you go down, now here is my landmark, right? This is my landmark. Okay, so if you choose any point which is farther from your landmark, then the distance, so like suppose my X is farther, it's is somewhere here, right? So the distance from the landmark means this distance becomes really huge, and if you take the square, then this quantity, this whole quantity becomes very big, right? And for any standard deviation you choose, this quantity is still big. So the e to the power negative of very huge number will give you, and will give you value close to zero, right? So the graph of e to the power negative number is looks e to the power minus x is like this, right? So if you are so this is the graph for e to the power minus x. So any value which is like towards the very much negative, so if you go for e to the power which is very negative, you will get value almost close to zero, right? And you talk about any point which is closer to the landmark, right? So like if you take a distance between these 2 points, and the distance between these 2 points is really less, like it is somewhat around here in this range, then if you take e to the power of negative e to the power of a smaller number, you will get some positive value, maybe some value over here, right? So with this trick or with this method, we can choose a landmark which will like suppose like these are all the green points and these are all the red points. So I can increase I can get all the for all the green points I can get positive values, and for all the red points I can get values close to zero. Then I can pass a hyperplane from here which can properly differentiate between red points and the green points, right? So this is what Gaussian RBF kernel helps us to do, right? Suppose so like suppose this was my data. This is not linearly separable. I cannot draw a line which can separate these two data points. So I am choosing a landmark L for landmark somewhere here, right? Then for all these green points I am able to draw all these green points. I will get some higher value like this in the z direction, or in the third dimension I will get some higher values. And all these red points which lie farther away from the landmark, I will get zero values. So all my red points will lie on the plane over here, but all the green points will, after some adjustments of the landmark and choosing the correct sigma value, all these points will be lying somewhere here. They will have a positive z value, right? So how does it work? So this now sigma, if I choose sigma correctly, then I can exactly cover this area until where I have green value. I can actually cover all the green points, right? So varying this value of sigma will allow me to increase the size of this circle, right? So if I increase the value of sigma, I can cover more green points, and if I decrease the value of sigma, I can cover less green points, right? So I can adjust the value of sigma experimentally to cater to all the green points, right? Because I want all the green points to lie in this top peak part, and all the other points to lie in the zero, like or to lie in the base plane, right? Now this trick also allows me to like have suppose my data looks like this, where there are like distribution looks like this. I can set up two different peaks, right? Because there is no one single peak, there are two different peaks. So I can set up a kernel function like this, where I will take the distance from one peak and I will take a distance from another peak. So all the points, all the data distribution which is are near to these two peaks will get separated, will reach to the top, will have a high z value, and all the points which are farther away from these two peaks will have a low z value. Then I can create a separator like this. So if this thing is positive, right? So this is the z direction. If my z value or the value after this transformation is positive, then it belongs to the green class. If this value is negative, it belongs to the red class. Similarly, if I'm applying two functions, then if this value is greater than zero, then it belongs to the green class. If this value is zero, then it belongs to the red class. So it's a very nice trick which allows me to classify non-linearly separable functions also. So there are some different types of function. The Gauss RBA function we have seen just now, is the mathematically it looks like this, and the shape is like this, like a normal distribution function. So like any data point which are lying here are transformed to the top, so that I can fit a plane from here to separate from the other classification, other class, right? There is also a sigmoid kernel, where like all the data points which are lying towards one end, towards the right, can belong to the green class. All the ones which are belonging to this end can belong to the red class, right? So it will transform my data in this shape. And we also have this polynomial kernel which will transform my data in this particular shape. Suppose we have multiple classes, so like one class can belong to here, other class can belong to here, and the other class can belong to third class can belong to here. So I can have polynomial functions also. right? So with this with the help of these kernel functions, we can do transformation of the data, and I can classify even the non-linear separable linearly separable functions also. Okay, so thanks a lot, guys. This is all what I have to discuss in the theory part of support vector machines. Next will be a Python implementation of support vector machines. I'll see you there. All the best. Thank you so much.